All right, today we are getting into one of the most powerful, most complicated, and honestly, most incredible machines humans have ever built, the liquid-propellant rocket engine. These are the engines that literally opened up the cosmos for us, and we're going to figure out how they actually pull it off. When you watch a rocket launch, you're seeing this unbelievable display of controlled, explosive power. It's just sheer brute force. So how on earth do you tame an explosion that's powerful enough to fight gravity itself and win? Well, that is the secret genius of the liquid propellant engine. So, first things first, why go through all the trouble with these complex sloshing liquids? Why not just build a giant solid fuel rocket, basically a massive firecracker, light the fuse and just stand back? Well, the answer really boils down to one absolutely critical word: control. Okay, think of it like this. A solid rocket, it's an all-or-nothing deal. Once you light that fuse, it burns until it's empty. You can't slow it down, you can't stop it. But a liquid rocket, that's more like a car. You've got a gas pedal, you can throttle up and down. You can even turn the engine off completely and then restart it later. And that control, that's what makes everything from landing on the moon to landing on a drone ship even remotely possible. Now, despite all their mind-bending complexity, the basic idea is actually pretty simple. You've got a tank of fuel, a tank of oxidizer, which is basically just liquid oxygen to let the fuel burn in space. You use some seriously powerful pumps to blast them into a combustion chamber. They mix, they explode, and all that hot gas shoots out of a nozzle, pushing the rocket up. So we're going to use this simple idea as our guide to explore the three huge engineering problems they had to solve to make this a reality. So let's jump into that first big problem. What do you burn? Choosing your propellants is this constant, tricky balancing act between raw power, safety, and just how complicated you're willing to make things. And what engineers figured out pretty fast is that there's no such thing as a perfect fuel. On one side, you have cryogenics, like the liquid hydrogen and oxygen that powered the space shuttle's main engines. They give you amazing performance. But the catch is they have to be kept insanely cold, which adds all sorts of weight and risk. Then you have storable propellants. These can just sit in a tank at room temperature for years, ready to go. A lot of them are hypergolic, meaning they just ignite the second they touch each other, which is super reliable, but they also tend to be incredibly toxic stuff. And that brings us to the new kid on the block, liquid methane. Methane kind of hits this sweet spot. It's got better performance than old-school kerosene, it's denser than hydrogen, so your tanks can be smaller, and, this is a big one, it burns really clean, which makes reusing engines so much easier. It's really no surprise that cutting-edge engines like the SpaceX Raptor are designed to run on it. Okay, we've picked our fuel. Now for the second great challenge. How do you move literal tons of this stuff every single second into a combustion chamber that is already a raging inferno of immense pressure? And this is where the simple diagram meets a brutal reality. Remember that nice, clean illustration from a minute ago? Well, this is what it actually looks like in real life. It's just this unbelievably dense maze of pipes and turbines and valves that has to handle insane temperatures, pressures, and vibrations all at once. So, how in the world do you make all this work? The answer is a true engineering marvel: the turbopump. The best way to think about it is like a tiny but absurdly powerful jet engine. But instead of pushing a plane forward, its only job is to spin a set of pumps. And these things spin at tens of thousands of RPM, forcing the propellants into the combustion chamber with just incredible force. It's really the heart of the whole engine. But wait, what powers the turbopump itself? Well, there are a few ways to do it, and engineers call them engine cycles. The simplest is the gas generator cycle, which is what the giant F1 engines on the Saturn V used. It's basically a small, separate rocket engine whose only job is to power the pump. It works, but you waste that exhaust, so it's not super efficient. On the other end of the spectrum, you have the staged combustion cycle from the space shuttle. It's wildly efficient because it routes all the exhaust into the main chamber, but my God, is it complex? So we have our fuel, we have a way to pump it. And that brings us to the third, and maybe the most dangerous, challenge. How do you mix and burn all this stuff in a stable, controlled way without the entire engine shaking itself into a million tiny pieces? This was the nightmare that haunted early rocket pioneers. These destructive vibrations, these combustion instabilities, they could just appear out of nowhere and completely destroy an engine in milliseconds. The massive F1 engine that took Apollo to the moon was almost canceled because of this problem. Solving it was honestly one of the greatest engineering triumphs of the entire space race. And the key? The secret to taming these violent forces is this component right here, the injector. Now, this isn't just a simple nozzle. It's an incredibly complex plate, sometimes with thousands of tiny, perfectly drilled holes. It acts like a super sophisticated showerhead, mixing the fuel and oxidizer into the absolute perfect spray pattern to get a stable, efficient burn. And man, have these things evolved. The early VT rocket used really simple jets, not very good. Then came the pintle injector, which is this really clever design used on the Apollo lunar lander, and get this, on the modern Falcon 9 Merlin engines. It gives you amazing control. And then you have the absolute gold standard, the Space Shuttle's RS-25 engine, which actually turned the supercold propellants into gas before injecting them to get nearly perfect stability. You know, solving these three massive problems, it wasn't the work of one person or even one country. It was this incredible, decades-long global effort, built on the dreams of some truly brilliant pioneers. It really all started as just an idea, a theory, back in 1903 from a Russian scientist named Konstantin Tsiolkovsky. Then, in 1926, the American professor Robert Goddard proved it wasn't just a dream, launching the world's very first liquid-fueled rocket. The technology took a really dark turn in the 1940s with military applications, but the engineering knowledge gained from that era eventually led to the mighty Saturn V, the machine that finally made Tsiolkovsky's vision a reality. And if you need any proof of just how dangerous this early technology was, just look at this thing, the Messerschmitt Me-163 Comet. It was the only rocket-powered fighter plane to ever see combat. It was blazingly fast, but its hypergolic fuels were so volatile and corrosive that they were often a bigger threat to the pilot than the enemy ever was. But the history of rocketry is full of unsung heroes. Wernher von Braun himself gave credit to a Peruvian pioneer named Pedro Paulet, who claimed he had actually designed and tested a liquid-fueled engine all the way back in 1897. It's just a powerful reminder that the dream of spaceflight is a truly human story, spanning the entire globe. So what's the big picture here? If you remember three things, make it these. First, the real magic of liquid rockets is control. Second, every single design choice is a tough trade-off. There are no easy answers. And third, maybe the greatest challenge of all wasn't just creating the power, but learning how to tame the incredibly violent forces inside the engine itself. From Robert Goddard's farm field to the dusty surface of the moon, and now beyond, the liquid rocket engine has completely transformed our world. And today, with things like 3D printing and brand new fuels totally revolutionizing how they're built, you just have to wonder, what new frontiers, what new worlds will this amazing technology unlock for us next?